So, welcome back to my lecture. I will spend approximately 10 minutes on our ideas how to improve time-dependent density functional theory or density functional theory-based methods for calculating excited state. And then I will switch to spin-orbit coupling, and for the rest of this lecture and all of the next lecture, it will be about spin-orbit coupling and intersystem crossing. So I told you there are certain problems associated with TDDFT, and the problems are mainly associated with TDDFT because the exchange interaction is not properly taken into account in these methods. We can start with a completely different wave function based method, multi-reference configuration interaction. So the idea of multi-reference configuration interaction is that you build a linear combination of configurations. Looks awful, but it's very easy because you have coefficients here which are linearly varied, and so the method as such is much easier, so to say, to understand than time-dependent density functional theory. So in this C0 here, or C0, you have the most important configurations that you need to describe your ground state and your excited states. And from there, you allow all single excitations, in this case from orbital A to R, double excitation from AB to RS, triple excitation, and so on. And if you allow for all excitations, this is, of course, the exact solution. As I said, these are single excitations, double excitations, and very often this problem is, so to say, truncated here at the double excitation level. The coefficients are determined from a secular equation. It's quite easy. So you set up a Hamiltonian matrix, you have a coefficient matrix, and then you solve for that. And you can ask, so to say, the program for 10, 20, 30 roots out of a few million, which the dimension of that Hamiltonian matrix is a few million. But if you just ask for the lowest state, you will get solutions for the ground state and for all the excited states. And the good thing of this method is that you have a real upper bound on the true ground state energy. You can improve this method systematically. So if you feel that the double excitations are not sufficient, you can go to triple excitations, quadruple excitation, at least in principle. So for a complete expansion, you get the exact solution for a given set of basis functions. But of course, this is much too expensive to be employed for any meaningful applications. You can get that for atoms, small molecules, but not for the big ones. And what is particularly expensive is so-called dynamical correlation. This is a type of correlation that describes the tendency of the electrons to avoid each other. You can understand that electrons which repel each other, they do not want to be close together, and this is something which is completely neglected in Hartree-Fock theory and only partially taken into account in density functional theory. So we have very long CI expansions for this dynamical correlation, but we excellently get all these multi-reference effects which are not included in density functional theory. So the idea was to take the good results from both worlds. So the idea was MRCI describes all the static correlation. The multi-reference effects are described excellently by MRCI. As I said, the expansions are very, very long for the dynamical correlation, but we know that density functional theory does a good job. Ground state density functional theory, not TDDFT. Ground state density functional theory does a real good job on dynamic correlation. And now we try, so to say, to combine both. And in this combined approach, we have to, of course, to take care that we do not over correlate. So the dynamical correlation that is included or would be included by MRCI, because I said if we expand it in a very long time, everything is correct. We get the exact solution, so we also get dynamic correlation. So we do not want to have this double counting of dynamical correlation. And this was the starting idea. And so this method is a parametrized method. It has a few parameters. It's not like a typical semi-empirical method where you have coefficient and parameters for each element, so to say. But here you have only a few parameters, 4 or 5, for all the elements. And these are fitted to experimental data. So it's not a full ab initio approach, but it's a wave function-based approach which works, so to say, very well. So we start from the expression with Hartree-Fock. This is just the Fock matrix for the Kohn-Sham Fock matrix again. And then we have, so to say, diagonal elements in this matrix. We have off-diagonal elements which have the same space part but different spin parts. And we have, so to say, off-diagonal elements which differ both in spin and spatial parts. And the details of this Hamiltonian are not very so you don't have to pay attention to that. Just pay attention to these red factors. So this is, so to say, the original Hamiltonian. Then we replace all the Hartree-Fock elements by their Kohn-Sham counterparts. And by this replacement, we get a lot of the dynamical correlation energy. Then these are the Coulomb and exchange interactions, which you find in this normal Hamiltonian. And you see these are scaled by parameters Pj and Px. And these are two parameters which are then fitted to experimental excitation energies. And the same is true for the off-diagonal elements. So for the off-diagonal elements with the same spatial part, you have 1 minus Px. And then for the off-diagonal elements, you have here a damping function. And this damping function takes care of that you do not double count correlation. It's a function, so to say, that falls off very quickly, very steeply with the excitation, with the energy gap between two functions. And in that way, you get a method. You have here P1, P2, Px, and Pj. So there are 4 parameters for all kinds of states and all kinds of elements. And there is a selection threshold, so to say, also cutting or truncating the long CI expansion so that we get a reasonably cheap method which does not have all these problems which I described for TDDFT. And this I showed already quickly this morning. What you see here is the error distribution. 0 error are the experimental energies of approximately 140 or 160 electronic states. And you see that the method peaks quite well, and the width of this Gaussian here is In this case, the root mean square deviation is 0.15 electron volts, and here we have plus 28 and minus 0.39. So even in these flanks, the errors are not so large. And the numerical values of these parameters, of course, depend also on this selection threshold. And what can you get from these kind of methods? So what I show you here is a typical complex, which you could also have. In this case, it's a phosphorescent copper complex. You have a phenanthroline here, a copper, and an N-heterocyclic carbene. And what I show you here is an absorption spectrum. The black line is actually the experimental absorption spectrum by Krylova, and Thompson is also involved here. And the green line here is the envelope of all our transitions. And you see that the green line follows the black line almost perfectly. So there's a very, very small shift, but you can essentially reproduce this absorption spectrum, and you see how many individual transitions you see below these lines, but it tells you that the method works very, very well even for this large kind of copper complexes. For all the transition metal complexes, I would recommend that to include relativistic effects. You may think, well, copper is a light element, so you don't need it. Relativistic effects are rather large for copper. So the D levels and the S orbital levels, they shift quite a bit whether you include relativistic effects or not. You can do that by using relativistic effective core potentials. And that is what is normally done in all the standard programs. So you just have to take care of that. Also, I recommend to do that not only for the heavy elements, but also for the first row transition elements. So coming back to the spin-orbit coupling. So even spin-orbit coupling has an effect on the excitation energies. It's not only on the coupling, but it also can shift state. And this is shown here for the gold complex we were talking about this morning. So this is what we see from time-dependent DFT. This is a torsion angle of 90 degrees. This is a coplanar arrangement of this gold complex. If we do a multi-reference effect, we level out more or less here the singlet state. So the energy difference between the perpendicular and the coplanar orientation is no longer very large. And then when we include spin-orbit coupling, in this case here, you see that here you already see a blue shift. And you shift a little bit further, and also the states come closer. And of course, only if you include spin-orbit coupling, you can calculate phosphorescence rates and inter-system crossing. So in this case, even the spin-orbit coupling changes the singlet-triplet gap. And you should consider that always if you go to third row transition elements. It's not necessary for first row, it's not even necessary for second row, but for third row, if you have iridium, platinum, gold in your complex, I recommend to put relativistic effects and also spin-orbit coupling, so to say, in the calculation of the energies. And with that, I conclude this, this part, and then I come directly to spin-orbit coupling.